Recording in progress.
এটা মানে যখন কোর্স অ্যালটমেন্টের ওইসব যে সার্কুলার মানে প্রেফারেন্স ওই এর প্রশ্ন, তখন সেই নোটিশটা ইয়েতে মানে আমি এটা লিখে দিয়েছিলাম যে মানে অ্যালটমেন্ট ঠিক আছে যা দেবে, কিন্তু দ্য পয়েন্ট হচ্ছে যে মানে আই অ্যাকচুয়ালি will not be technically there for the entire semester, মানে টিচিং পিরিয়ড। কোথাও যাচ্ছি এরকম নয়, কিন্তু এখানে আমি তো কন্ট্রাক্টে ছিলাম, so the 5 year ends in April. Therefore মানে আর কি somebody has to মানে take some action আর কি। মানে whether or under what conditions would a renewal be possible, এই আর কি। Some technicalities which I should start out with, that the final all right, so need to settle the official things first. So the final exam, whenever it is, will be entirely on the second half of the course, that is critical phenomena plus RG, that is not mean field, which was essentially the mid-sem. So not, it is essentially the RG functional integrals, perturbation theory, Gaussian business, which is related to functional integrals, and RG, whatever we. So basically, it is that part of the course which you need to know for the exam, and the other is the Boltzmann transport and plus Langevin equations. So that's essentially the reasonably equipartitioned, maybe 10 to 20% errors in equipartitioning, but no more than that. What to try out? Should I go? All right, so that's that. No, no, ওই যে যা বললাম একেবারে প্লাস লাঞ্জেভা, Boltzmann transport plus লাঞ্জেভা একেবারে তাই, লিটারালি নো ফোকার-প্ল্যাঙ্ক। পরীক্ষা দেওয়া যায় না এনিওয়ে, ফোকার-প্ল্যাঙ্ক। কোনটা? ও আচ্ছা, মিরর, রাইট। হ্যাঁ, সেটা তো লাঞ্জেভা। All right. So what I want to do is talk about various things, not too detailed, but just to make you aware of certain things which we haven't talked about, but which are. So these all come under the head linear response theory, and the point is that I have a system which I perturb slightly and look at how it responds. That's the game. So what am I supposed to, what is one looking at? Well, if it is, let's say I have an isolated classical system, and there is some, it is described by what one normally would call generalized coordinates, but let's not even think about, I mean, general, just some plain xi coordinates which describe the isolated, and they would have dynamics, some kind of, each one of these i's would have some dynamics which can be written down as x, each of them through some Newton's law as xi double dot plus some function, let's say g of I of the set x and the set x dot equal to 0. So that's acceleration equal to external force. The external force can depend on position, can depend on the velocity, so which essentially means friction is included. So that's why so it could be this, or it could be a quantum system or it could be isolated and classical, quantum. And you would be looking at an evolution of a state, described by some wave function and the existence of a Hamiltonian. And what you are interested in this case, as what you actually see in real life, are the certain operators which are important, say a set of OIs, and what you calculate are the average values of these operators. So over here, it is the dynamics of xi, which you can calculate. Over here, it is the expectation value of the operators OI corresponding to the physical quantities, which. And now I have this system and I perturb it. So whether classical or quantum, I perturb by force some F. So the system will have to respond. And the response is going to be, it is this response which we are after, and this is going to, response would mean that the xi's change. There is going to be a change delta xi. Over here, there is going to be a change in the expectation value. And what I want, the regime I want to work in is where the delta xi is proportional, is dependent on linearly on the f. That is, in other words, delta xi is alpha ij fj if all these have I mean, if I have several i's and several j's, I mean, this would have to be delta xi equal to alpha ij. Similarly, over here, it's the same story, that it is some alpha ij once again, which is its own, and right. So now, what exactly do I mean? I mean, for example, always worthwhile to have an example in mind, that what am I talking about? Suppose I'm talking about a magnetic system over here, and I apply a small magnetic field. So the system will respond by showing a change in the magnetization. So it is the alpha ij, therefore, is a susceptibility. So the typical way in which I disturb a magnetic system by switching on a bit of the field, and the system rests. So what these alpha ij's are generally written as chi ij's, chi because in some sense every response is a susceptibility. So chi ij is what one writes. Now, what can I say about the business? So I'll drop the subscripts. I mean, those will only add for clutter and also errors, but which and so what can I say? The response. So this response is going to be obviously the xi's time developed, the delta oi's. This is it's all, let's say, Heisenberg picture. Operators time develop. So operator expectation values time develop, and so which implies that the picture that we are working in is a Heisenberg picture. And over here, I don't have to worry about any such thing. It's the system, whatever I'm interested in looking at, that's changing it. Very good. So it's changing with time. So it is the change values now happily drop the x of t. What x of t? That which was caused by this f over here. So I'm going to write it as an integral chi of t minus t prime f t prime dt prime. So this is the definition of the response function. X of t, I mean, this is capital F, better writing small f is easier. So that is my x of t as chi of t minus t prime. So it is t obviously has to be greater than t prime, something which happened before t at time t prime, which is before t, and you are looking at the response for that. So it is chi of t minus t prime. It is tacitly, it is all t which is greater than t prime. The integral over t prime goes from minus infinity to t.
This kind of functions are impulsive.
Are
Impulsive means happens for a short time.
No.
It's just a function of just a function of time.
Yeah. So it's f of t prime. Random যদি করি তাহলে random হবে, কিন্তু don't মানে না মানে as I said, it does not need to be random. It can be just a static magnetic field switched on. So the action, then the time, what is the time dependence? I switch it on at some time. Kintu it can be a time dependent magnetic field. So that's entirely possible. It can be I want to look at, so I have a H and a T. It can be a H which looks like this. It can be a H which looks like this. It can be a H which looks like this. It can be a H which looks like this. Jakichu. So it is all contained. I mean, I'm simply saying that there is, I'm subjecting the system to some external force, external effect F, which is perturbing the quantity that I was monitoring, the xi over here, the operator oi over here. And it is all in a linear, I am completely in a linear response theory, so that the x is determined only as a linear function of the f. So the response, and therefore this response that I'm looking at is a linear response. It's a linear response because I have only f. So in general, I mean, it's a small f producing a small x. So a small f with producing a small x over here as a response, and it's simply that I have the delta that I had over here should have had either you write just delta, or I, to be sort of correct or careful, I should have put a delta over here. That same order of magnitude. Whatever the f is, the order of magnitude, x is the same order of magnitude. I'm talking about a small f so that I can talk about a linear response. So whether it is this or whether it is that, my x of t, it's the response is going to have a form which looks like all that this is saying, that it is causal. T is this relation over here. Similar relation would hold for delta O. Delta of average O would also look exactly like that, and all the content of the right hand side is that everything is happening before T. All right. So very good. So, I mean, what this is telling you, that I'm in the business, so where will it take me? It will take me to susceptibility. It will take me to this. It will take me to all the transport coefficients, because there it is a particle current is d and dz. Heat current is, a heat current is thermal conductivity dt dz. Momentum current is is viscosity times so a momentum current would have a PIPJ, momentum with velocity, and that would be eta with a del VI del XJ. So that it's the viscosity, the conductivity, all these are responses, and better write some other. Anyway, whatever. J particle, maybe. Anyway, so electric current, it's the electric field producing it, it's electrical conductivity, magnetic susceptibility, particle diffusion, heat conduction, velocity, momentum transfer in a fluid. So all of these, I mean, are of the same category. These, well, actually, I mean, one can, I mean, which we actually define things like viscosity or diffusion also in quantum theory. So, I mean, there is a meaning, I mean, simply because a conductivity can be defined in a quantum system, so can actually the viscosity be defined. So all these early universe stuff where viscosity does come about, and the for calculation that one uses is actually a quantum prescription for calculating those viscosities. So one that is, this is we the yeah we won't be, because we won't be talking about it explicitly. It would be mainly talking about one in these contexts. One talks about primarily things like conductivities and susceptibilities, but the point is, what it is, there cannot be too much of a difference, because over here you are asking how expectation value changes. How the expectation value changes is going to be determined as by tell you why. Why it is not all that different. The point with over here is that when I'm talking about classical things, then it's also obvious that it is change a magnetic field, the magnetization changes. Sure, I mean, it is M over here, H over here, and that is that. And now if I were to change this, then if the expectation value is going to change, because I have made some change in the magnetic field, for example, in this in a system, then the point would be that what I would be looking at is quite, I mean, the way quantum mechanics should go, I mean, that it would time develop, and what you would be looking at in the response should be something like a 2-point correlation function of T and T prime. So it would, the chi over here is expected that it is going to be this delta O is, you have a delta over here, change in the expectation value, and the change in the expectation value, when you try to do a calculation of that, should turn out, I mean, the you look at how the Schrödinger equation, you look at, there is a, you are adding a perturbation to the Hamiltonian. The perturbation is what is being through this F over here. So there is a perturbation. That perturbation is going to cause changes. So there is going to be a time development in quantum mechanics through the interaction part. There is going to be an interaction part of the Hamiltonian, which is what this the extra perturbing force brings in, and the interaction part of the Hamiltonian causes, there is this interaction picture where the operators, these unitary operators which correspond to time development, change according to, I mean, the, yeah, this IH, DU, there is some kind of the commutator between the U and the interaction part of the Hamiltonian, right? So and that is the part where, I mean, you pick up this correlation function, and that is that's not a surprise. That's not a surprise, because when we were doing Ginsburg-Landau kind of stuff, the susceptibility worked out to be the MR1, MR2, right? I mean, that was the correlation function integrated over all R12, which gave me the susceptibility over here. So that is why, I mean, the analog is for this is also over here we were doing a static spatial theory, so it was this. The quantum business is going to be, I mean, and right now, I mean, when we will do the linear response for the classical as well, we'll see that tacitly it's all going to be a time-based issue. So it's so that's the operative part. All these correlation functions. So therefore, there is, I mean, just as you can talk about electrical conductivity in the quantum problem, you can also talk about what is a viscous response in the quantum problem. So the QFT has a there is a meaning of viscosity in a quantum field theory. That's the driving home point. That you might you wouldn't normally think of it, that viscosity appears so clear-cut classical, but when you, I mean, it's a process. No, it's a momentum transfer process. And there is nothing which says that in a quantum system, there won't be momentum transfer. Right? I mean, so there it is possible. So and the greatness of these, I mean, the good thing about these way of dealing with responses is that it automatically gives you the quantum expressions for what a viscosity or conductivity should be. The best, one of the nicer places to look it up is Tong's kinetic theory lectures. Parse it out carefully, so I mean, you can see the
quantum viscosity in quantum theory. Does it have any separate name or
viscosity?
What kind of problems in what kind of system those viscosity appears?
What kind meaning?
Can you give any examples of certain systems where this kind of terms?
Oh yeah, I mean, as I said, it's basically the early universe stuff where things were, I mean, these high-speed flows decelerating and so on and so forth. And so then you would be able to define, I mean, viscosity, and it plays a role in the time development. Yeah. So there was a bound which I'm a bit that a few years ago was popular, viscosity bound on some process in the early universe. Anyway, but yeah, but it's viscosity has its uses. Right. So it is a question of this chi of t minus t prime ft prime. So that's the linear response that one is after. All right. So now the point is that this, you see, looks a little bit of problematic in the sense that It's integral which has to be done over a whole set of time, I mean essentially from -infinity to t. Life is much simpler in the Fourier space. So what one does is look at, now tacitly this over here can actually be, all right, let's do it slowly. So chi of t minus t prime ft prime dt prime, that's this x of t over here. I want to define Fourier transforms f omega, so that I want it's a sign which is going to be important, and so ft e to the power, if I define it with e omega t dt, then it is the f of t is integral d omega over 2 pi e to the power minus I omega t f omega. So that's the definition with which we will be working. So f omega defined as this, f of t defined as that. So that's the Fourier transform in this. So I want to look at e to the power. So I want to look at x omega. So I want to look at x omega. X omega is equal to integral xt e to the power I omega t dt, which is equal to x of t, sorry, it is chi of, so the x of t, better put the x omega over here, and that is from some, its overall time, and then comes the x of t over here, which is -infinity to t, chi of t minus t prime, and then it is f t prime, and then it is that's xt, x of t, and then it is ft, what am I after? It is x omega, which is xt, which is should have had the dt prime over here, and then there is the e to the power I omega t, and there is dt. Very good. All right. So now I'm going to write this as so it's an x omega, which is t integration over here. There's a dt prime over here, and it's that which I want to transfer, all right, here. So chi of, it's a chi of, so I need to go to chi of omega. So chi t minus t prime is going to be chi of omega, and this is going to be e to the power
Science has contributed
minus I
important
omega
for
t
regulating
minus t
a lot of what we
prime,
call
and then there
post-processing
is
to look at the data. And what
2 pi,
post-processing
there
means is
is
simply any fancy
d
post-processing.
omega.
We actually were able to see a signal with our naked eye. Of course, the first thing we thought is that there's artifact and there's something wrong, because this just is not
Sure.
something
I
that
mean,
we
this is
typically would see. And so
I'm
then
doing
we
x
had to go
omega,
through the
which
entire
is e to the
reporting
power I
system and
omega
take everything
t,
apart
and now
and put it
I'm
back
doing
together
this. I should
before we
have had
convinced ourselves that this is actually
for
real. Then
this over
when
here,
we
it
discovered
is
that it
chi
was real, it was
omega
really
e to
quite
the power
amazing
I
because
omega,
nobody had ever seen these kinds of signals
and then
before
it
for
should
this.
be a 1 over here, and that, and then I have that's my f e to the power I omega t. There is f t prime, and there is e to the power I omega t. There is dt prime and dt over here. All right. So it is. So I take dt. Huh? D omega 1. Integral sign লাগবে। ঠিক আছে। So there are three integrals over here, d omega and omega 1. So let me do the integral over t. If I do the integral over t, then it is going to be it is an integral which is going to be e to the power minus omega 1, and this is going to give me a delta function, right? It is e to the power I omega t, and e to the, I'm looking at e to the power I omega minus omega 1 times t and integrated over dt. So that gives me a delta function. So dt, that gives me a delta function of omega 1 over omega. So I have when I do this part over here, and now I'm left with t prime. Part. Huh. No, the point is that there is a, I have to, I can, the integral over there is a d. Achha. So what you are after hoche, this is xt x omega, which was xt e to the power I omega t. This is a integral which runs over dt going from 0 to infinity, right? This is over integral, this is t over all time minus infinity plus infinity. This is the definition of x over, I'm doing the integration over dt. So dt integration is what I'm doing, it runs over minus infinity to plus infinity. So there is so now what, there was this question over here that there is a chi of t minus t prime over here. So there is this integration which has to stop at time t because what I'm looking at is essentially, so chi of if I'm going to look at the response which is beyond the time t, this is essentially, I could, I mean, there is no response. It's an integral over t prime over here, which is stopped at time t, because that is where I'm looking at it. It is because I have put a chi t of t minus t prime over here. But if t prime is going to go beyond t, it gives me 0, and therefore this integral top limit is effectively infinity. You see, chi of t minus t prime is equal to 0 if t prime is greater than t. So this integral, which is up to t, is actually infinity. I mean, chi of t minus t prime, chi is a response at a time t which is greater than something happened at time t prime. I'm responding to it at time t. That is the response function chi of t minus t prime. So causality tells me that if t prime is greater than t, chi is 0. Therefore, this integral on dt prime is actually infinity. This t has no value. Formally, I wrote it like that because that is the way, I mean, one would be writing it. But then you realize that t prime, I mean, chi is 0 if t prime, which is over which I'm integrating, is actually greater than t. So this integral is as good as writing t equal to t prime ta সব সমান well, chi of t minus t prime is 0 if t prime is greater than t, and therefore this integral is up to infinity. তাই জন্য মানে I'm not bothered আর কি. So I'm doing the integration over t, so I don't need to, which I mean, good that you brought it up. I'm not being I'm not really caring, because with the chi there, this integral is actually going up to infinity. The chi is causal. So it is yeah. So where was I? It is e to the power, there is a delta of omega minus omega prime. So what this chi becomes a chi of omega. And now I have the t prime. So ft prime e to the power I omega prime t prime dt prime with dt prime running up to 0 to infinity. So that is the Fourier transform f omega. So and therefore x omega is equal to chi omega times your f omega. So x, the response in time space is non-local. All times before t prime, I mean all times before t are contributing to x of t. But if I look at it in Fourier space, x omega is equal to chi omega f omega. So the response is, the linear response is completely local. I mean, that is why you essentially like working in frequency space. I mean, it's a local response over there. So manipulating is so much easier. So I define a susceptibility in real time. I define it through an integral equation. I define a susceptibility in frequency space. I define it through an algebraic number. And now the point is, that suppose I do an experiment. What is the practical use? Suppose I do an experiment and I find that this x of omega is not following this relation. That means the linear theory is no good. You are actually working in a nonlinear regime. So where the linear response has broken down. So that's where the practical utility of this is. That, I mean, you can, I mean, generally you do carry out measurements which are very often in frequency space, simply because, I mean, this is good indicator. I mean, this is easy to work with. And the moment you see deviations from there, you know that this is a linear response, and it says that linear response is no good.
Therefore, the electrical means the non-linear circuits use this frequency domain.
Yeah. Wrong কিছু না, এটা is a linear, মানে if I could not write this, if xt did not respond linearly to f, which is what this whole relation is, তাহলে পরে এইটা হতো না। এবার এইটা হয়েছে কি হয়নি সেটা প্রুভ করা সম্ভব না, মানে এইটা সত্যি না মিথ্যা তোমার সিস্টেমের জন্য সেটা জানতে গেলে আমাকে একটা ইন্টিগ্রালের কথা জানতে হবে। Whereas you do a measurement at a given frequency, measure যে এটা যদি হয়ে থাকে তাহলে ঠিক আছে, যদি হয়নি তাহলে গেছে। ঠিক আছে না? So that's so linear response, valid or not valid, determined and completely by, do you see this or don't you see this? কি করে থাকবে? আরে এটা সবকটা ইন্টিগ্রাল হয়ে গেল। All right. X of t is equal to integral chi of t minus t prime, and it is f of t prime dt prime. So this is from your the integral over t prime, which essentially goes from minus infinity to plus infinity, because chi of t minus t prime equal to 0 if t less than or t prime greater than t. So I can go ahead and write this causal minus infinity plus infinity. Now you are looking at this part over here, and what I'm doing is writing this as chi omega. So this becomes minus infinity to plus infinity. Chi of, there was a delta function na jeta killed the integral. So, all right, I have a linear response business which tells me that x omega is chi omega f omega. So I have a linear response characteristic going like that. Achha. Next thing which is important about this is one needs to talk about to pick up already go with this. Do it slowly. All right, fine. The next thing which one needs to worry about is that this if there is a standard example of this chi omega which is very useful to have a simple harmonic oscillator which is responding to external force. But there is, so that I certainly need to, oh God, worry about, or maybe that I'll leave as a, will take me a little time. Something, all right. We look at the properties of this in the all right. The chi of omega, which have got over here, this is coming from x of t, which was essentially minus infinity to plus infinity, chi of t minus t prime, ft prime, and dt prime. So this was the x of t, because with the provision that this chi of t minus t prime is 0 when t prime got to be greater than this. I want to look at the how do I calculate this chi of omega. Well, I calculate it by doing t minus t prime. So I want to look at chi omega as the Fourier transform. So I want to calculate chi of omega by doing minus infinity to plus infinity chi of t. This is the definition of the Fourier transform, I omega t dt. All right, so that's how I calculate. Suppose somebody told me what chi of t is in real time, then I would do this and get it. Give me a messy picture of chi. So I or let's say somebody, let's say, has done that for me. So I want to get chi of t. So suppose somebody has done this measurement for me, or the linear response business, and got me a chi of omega. I'm now in the business of getting, after all, it is the more practical thing is this chi of t. So you do want to do chi of omega e to the power minus omega t d omega, correct? All right, so I'm armed with chi of omega and want to get this. So how do I do this? This is a complex, this is an integration with that I sitting over there. So the natural thing would be one of those complex integration techniques that you have learned, which will do the job? Huh? So let's say I want to do that. So what will I do? Now, chi of t, mind you, has has a constraint. Chi of t is equal to 0 if t is less than 0. Huh? So that was the t minus t prime that we were talking about. Huh? So chi of t equal to 0 if t is less than 0. So all right. Now I am trying to evaluate this chi of t with this over here, and I know that this has to be valid. So this is integral from minus infinity to plus infinity. So here I go along the omega axis, minus infinity to, so this is my origin somewhere here, minus infinity plus infinity, and I now go in the upper half plane. All right, I go in the upper half plane, so my omega, so upper half plane, omega has, forget the real part for now, it is plus I times, let's say, y. All right, so that's the imaginary part of so this part, e to the power minus I omega t is goes to e to the power yt. Correct? So e now, so but you are interested in t less than 0, right? So my interest is in t less than 0. So I'm quite happy that on this, if t is less than 0, then over this I get, when I do this integration over the this, so I go from here to here and then from here to here. All right, and I have picked up 0 from here, from the top. So minus infinity to plus infinity, this is, I'm operating in this region here, is equal to the residue at the poles. Huh? But if there is residue at the poles, this is not true. Huh? Because get the point. Huh? So I'm using Cauchy's theorem. Cauchy's theorem, I have got around this, and along this contour, the integral is just minus infinity to plus infinity along the real line, and then along this infinitely path over here, I have got 0 for t less than 0, only for t less than 0. And therefore, to be consistent now that this answer is chi of t is actually 0, I need to have no poles over here. So the theorem chi, this complex chi over here has no poles. Chi omega has no poles in the upper half. So that's a very strong result. It tells you that the real and imaginary parts can't be independent. I mean, I'm making a statement, I'm putting a constraint on the chi of omega. So I'm saying that it's real and imaginary part, it's the chi of omega has, that constraint is going to be reflected as, I mean, it has to come somewhere. It is chi is, this is a part that it's long, and you'll certainly see it in some course or other worked out. But this no poles in UHP means that chi, which is chi1 omega plus chi2 omega, there is a constraint on the chi, and therefore this and this cannot be independent. Chi of omega is this, and I'm saying that chi omega has that that, and therefore there is a constraint. This constraint is expressed as Kramers-Kronig relations. So you will find that the real part is related to the imaginary part, and the imaginary part is related to the real part by a pair of relations which are called Kramers-Kronig relation. A combined form of it is something that I will write down for you, which is handy. Is it? Yeah. Yeah. This is the answer. This is a particular form of Kramers-Kronig, which is you will find extremely useful as you sure maybe the limit epsilon tending to 0. This is a form of this theorem, which is because chi is chi1 plus chi2, this actually relates the chi1 and chi2. Yeah, but chi1 ta ekhane না না এটা কাই আরে কাইটা তো এইটা you see the point, you write chi1 plus I chi2 here, you may you notice that this can be written as the principal part plus the delta function part. So the principal part is the chi1 is the principal part of this without the epsilon, and when a chi2 has ঠিক আছে? All right, so far so good. কোনটা? আচ্ছা এইটা আচ্ছা আমি খুঁজে দেখবো তো, মানে দিস ওয়াজ শিওর। আচ্ছা না থাকলে মানে I used to have the hard copy এক সময়, কিন্তু that's been decades, so unlikely যে আর আছে। But anyway, যদি থাকে তাহলে মানে যদি নেটে খুঁজে পাই কোনো অন্য কনটেক্সট দিয়ে তাহলে দে, তা নইলে I look for যে if it's a so, all right. So now let's example would be x double dot damped oscillator 2 gamma x dot plus omega 0 square x equal to some f of t. So classical example would be an x double dot plus 2. Now what's interesting? I'll take technically one should solve it doing some, but I'll just cut corners here where we just don't have the time. So x, if I write, is a e to the power I omega t. If x is equal to a e to the power I omega t, then you immediately find that x of omega is equal to f of omega divided by omega naught square. So minus omega square plus 2I omega gamma. All right. So, and I have this with this as the ansatz, that is the solution for this quantity over here. I want to look at what is the amount of energy that I'm draining over. So this is a dissipative process. So the dissipative process, and if I have to have, if I want to maintain the system, I have to provide some, I have to do work on the system. That's it. Huh? So if I want to maintain things, I have to do work. So rate of doing work is power, and so this is the thing which I want to do and do quickly if I can, so that I can put in a word about something else. So I want to look at the rate at which, so rate of doing work. So I'm doing work, and the rate of doing work is going to be dw dt, and that is equal to f dot v. So this is f dot v over here. So that's my, so I have a, now it is some external force, which is, so it is f times x dot, so which is v, so which is equal to f times x dot over here. So x in omega space is equal to this, and this is the answer for that's the work done. I have to average. I mean, all these things will make sense only averaged over a cycle. So if I have all right, I mean, if f of t is equal to some constant f0 cosine of omega t, then it is the averaged over a cycle that I want to talk about. So it's averaged over a cycle that I want, and if I do the averaging over the cycle, I'll just write down the answer for you. That it's all a standard manipulation for getting there. So there's some answer which want to make a particular point. So, all right, okay. Let me, so I want to get this done, and at the end of the day, the answer should be 2, I mean, just check this out. Where is it written anyway? Sorry. Yes, right. What did I do? F0 square makes omega, and then, all right, imaginary part of chi there should be a I, so it's a imaginary, right, imaginary part takes care of this. So imaginary dw dt at a particular frequency. So dw dt at a particular frequency, if I do this general, it's what is the way of getting at it? Getting this general business is you actually write, you take this equation over here and you write x of t. So this is my, the answer would have to come through Green's, it is some Green's function g of t minus t prime times f of t prime dt prime. This is the response function, the chi that we have been talking about. X of t is chi of t minus t prime f t prime dt prime. That's what you put from over here. You get the x dot, and you then specialize to this f as f cos omega t, and the final answer should be this. That's where the chi of omega is the chi omega is simply 1 over omega naught squared minus omega squared plus 2 pi gamma omega. So just take my word for it that if you do this, that is what you will get. So this will be the imaginary part of chi omega. Now you notice that the imaginary part of chi omega is this. The imaginary part of chi omega is equal to minus 2 gamma omega divided by omega 0 square minus 0 square plus 4 gamma square omega square. That's the imaginary part of this. So, which means that what I have written down over here is the work that this external force is having to do. That work has turned out to be negative. And therefore, I have a problem. I have a sign problem. You see, that the point is that I should have had that when I have there is going to be a steady state setup, because there is this external force acting over there which will maintain the oscillations, and therefore the work done by this force over here, that would have to be positive and dissipated by this oscillator over here. I've calculated the work done by the external force, and I find that the answer is negative. Why did that happen? That I was careless about the importance of the phase over here. So this, I mean, all that it takes is write this as e to the power minus I omega t, and that would make it this. And why is that? Why is that careless? It is careless because of what I took the trouble of proving a minute ago, that the poles have to, there are no poles in the upper half plane. And the moment I say that this is the sign, I have poles in the upper half plane, and therefore I have a problem. So it should have been a minus over here as the response, and then everything is quite all right. So one has to be careful with these things. It may look like, I mean, or how does it matter? I mean, a plus or minus over here, but it does matter when these signs are concerned. That how much work am I doing on the system? Am I doing the work, or is the system doing the work? I mean, this has to be, I mean, the system, as soon as you have this, it can't do any work. I mean, it's dissipative. So, yeah. So that's, so all right. So that's something which is certainly interesting. One last bit before I get through. Let's see if I all right, so this theorem, the upper half plane, that is the big thing. Acha, 1 minute on this. All right, maybe one can do this. It's what I want is that what if I were, I mean, what we were doing is quite general. The structure, I took a classical case, and that works out in that fashion. If I do a quantum, worry about a quantum system, so quantum system in general terms, I mean, the reason this just want to spend, you'll find over the last few years, particular thing going around, which is OTOC, which is out of it is out of equilibrium correlation function. I mean, why did it become OTOC is anyway. I mean, it's something, but so this out of equilibrium correlation function has to do with what the same calculation that I was doing for this has to be done for the quantum system with that I have a H interaction. So there is the operator is some O, which I'm interested in, and there is an interaction term which is like it is proportional to OI, and let's say over here, what did I was here what was the coefficient with which put a phi as that? I see that. So so there is a H, there is some H0 which I don't want, but here is the coupling of to an operator O for the system couples through, this is the external effect, external field. This is like the external field. So the forget I, meaning that I could have several one of them. So a particular external field coupling to an operator of the system, which is this O over here. I have a H naught, and then there is an interaction term which has to do with an interaction with the external, so an agency. So there, and this operator O of the system couples to this external agency. So I have a phi O. In general, it is phi I. No. So what am I supposed to do? I'm supposed to now see what kind of a, as I said in the very beginning, that it is the expectation value of O whose change I'm going to, I want to monitor as a function of this phi over here. It is a small change in phi, a delta phi leads to a small change over here. So what's the procedure? The procedure now has to be, I need to propagate the system. I need equation of motion, equation of dynamics, and then I need to do a statistical averaging, and therefore there has to be a density matrix. To do the average. All right. So the dynamics would tell you that it is like, what I have to do is this interaction picture, and I need to do the following. It is there is this time evolution operator T0, which is the time ordered part of e to the power minus I, T0 to T, H interaction, and dt prime T prime, right? Always works. So now what am I after over here? I'm after that H interaction is small, and therefore I will expand this and linearize. Huh? So that's what. What is the time evolution? All right, just to keep things in perspective, the time, the IH du dt is just the H interaction times u, right? That's the right, and the wave at the psi of t0, that is equal to u t. The psi at time t is going to be this. Yeah, interaction picture, everything. So this is the interaction picture, and that is what I just want to point out without calculating. There is the, what I'm interested in now. This is the this is straightforward quantum time development. I have to do expected. My interest is in the average value of the operator OI, let's the operator O, and how that changed because I had this H interaction in. That's what my goal in life is. So if I want to do this business, then this O average has to be calculated as a trace over rho O. So that's that, and therefore this is going to be the it is a rho which has the I have to write this as actually rho. I put rho at rho 0, and the time developed this is rho of t OI, and I put rho at rho 0, time developed with this the O's over here. So it's either way. I mean, I can do time develop the rho, I can time develop this, and one way or another, and then I do perturbation theory. And so at the end of the day, something like trace of rho O going keeping at rho 0 and writing this as O U, then transforming this back, the cyclic business, transforming this to trace of U inverse, and then a rho 0, or do I want no, I don't want a U business, or do I can do it's a U inverse, so U inverse that should take me to right, that should take me to this time development, the U coming over here, which would mean a rho U inverse. I want to do a shifting. It's a U inverse and O over here. If I do that, then I would have to bring U over here. So that is just cycling. So I do U rho 0, U inverse this, and one more step, and yeah, so it was trace of this, that's correct. Now I want one more step. I want a trace. This is UOI0. Could have just worked with this, no? I simply then it would be, what do I want? I want this to be O at some initial time, and then so that would be with the rho 0. Acha. So this is why do I need it? I wouldn't need it. If I have a rho 0 U inverse OU, then all that I need to do is follow this part over here, and that should do the job for me. That this is trace of rho 0, it is U inverse O, and that part should, I want, it's perturbative. So I want to do, so it's a perturbation Hamiltonian. So it is going to be, this is all in the U over here is, all right. So what I do is I write U as, it is the perturbation part of it goes as, write U as e to the power, so 1 minus I, and should have been a h bar, forget it, T0 to T, and this H interaction, and T prime dt prime, right? So I write this as this part as this, and then there is your 1 plus over here, and so it is going to be the 1 giving you a rho 0, and then the correction term on 1, which would be a I, and there would be a dt prime, and it is a commutator between H prime and O. Yeah, so that's that. And but the commutator between H prime and O, and that is what is essentially, if this is these are at two different times, and the H prime is itself O, and therefore this is a commutator between O at time some t and O at t prime, commutator of that. So integrated over t prime with a I and giving me the answer at, so this is integrated over t prime, giving me the answer at t. All right, so it is this commutator over here, which is OT with OT prime, which tells you how this thing is going to behave. So this is that's that. So your delta. So now, I mean, this is O at some, where was I? I was at O of, at O at some time t, which I was calculating. The first term that I have over here with the u as 1 is essentially what this rho 0. So the rho 0 part of it, if you take it to the left hand side, the O which you have, the first term that you pick up, which is with the rho 0, is O at time 0, and then you have this correction over here, which is an integral over dt prime and is O at time t with O at time t prime commutator. And so it is this difference. What you have obtained is that difference in the delta O is proportional to this O two-time correlation function over here, and therefore the difference was defined as being the mobility of the response function that we defined was through the in all these places over here, there should have been that O connecting to delta O is the chi and then the external perturbation which you have, right? I mean, this delta O is delta chi times the perturbation that I put in, which is the whatever notation we had been using with this. So let me just. So the delta O was the definition of the coefficient is that there is a change in this, which is this the perturbing part of the Hamiltonian. So there is the perturbing part of the whatever is the F that we had in the classical case. There was a force on the right hand side, and my response is the delta displacement divided by whatever, assume that the force is small, whatever x it is causing is small, and x over f is the response. Over here, the quantum case, it is the operator O, which is small. It comes with a coefficient. The Hamiltonian part over here is O times some coefficient mu or lambda, something like that. And that is what you pick up over here when you do this, and that is effectively is the response of the system. So what is being said is at the end of the day that the response of the system is the expectation value of the commutator of t and t of the operator O at two different times multiplied by this. That is to say, this is the response function chi that we are talking about. The chi at time t has essentially become an integral over time t, and then an expectation value of OT prime and this over here. So that sort of there are factors missing here and there, but the basic point is there that it is this 2.2 time correlator of the commutator integrated over time causally to give you the chi of t, that is what is known as a Kubo formula. So the keyword, and that essentially is the vital thing in all these transport. If I am doing a quantum theory and want to calculate if I'm doing a classical theory, it is just commonsensical. I mean, you write down classical displacement, you know what the force is, and you do force displacement, and you get the response. Quantum mechanics is this operator, and the vital point there is the classical thing gets replaced by this commutator, two-time commutator over here. So that's the and the response of the system gets related to the commutator integrated over time, and that's that. So this is it's all the original Kubo. I mean, if you read the Kubo formula came in 1957, and the original barely looks like this, but today, if I mean, look at people talking about Kubo formula, you will always find that it is an expression which looks like this. And so, I mean, they all, it is just doing carefully the time-dependent perturbation theory, just done carefully to keep all the signs and so on and so forth. This part is, I mean, just comes from this. Key system? Sure. Yeah, right, sure. It's okay, sure. I don't think so. Mass expansion and convergence. This is the popular way of that. Whereas it goes back to it is Kubo reformulated, but Kubo pronota it looks entirely classical, and obviously when a commutator এগুলো সবচেয়ে সুবিধা হচ্ছে যে টং সুপার and similar আরো একটা আছে যেটা এই দেখবে যে আরো lecture notes which it's a continually evolving lecture notes. I think that's probably California, San Diego, but Aruba system. It's he updates regularly. It's that's worth looking at. And Tong is this is huge. Tong is classified by and when it does it very quickly. Right, it does it very quickly.
Even I mean, in similar in cheated things. Such a solution
খুব কঠিন হ্যাঁ it's not very easy হ্যাঁ সচদেব আছে অশ্বিন আছে and those are pretty lots of steps skipped but মানে এই Tom certainly does not skip steps. It Arovas is huge, so it does not skip steps. So yeah. All right.